title of our talk today, as you can see, is Climate Change and the Future Impacts across the Southwest region. I'm Darren McCollum. Robert Bohlin will also be presenting. I'm going to be talking about the global, larger scale climate change going on. And then Robert will come in and talk about what the impacts are locally in our area of the world in relation to this global climate change that is occurring. So let's get started. So what is climate change? Well, first, a definition. Climate change is any change in the long-term average of a meteorological parameter, such as temperature, wind, precipitation across a region. That can range on the scale of a decade to as much as millions and millions of years. It can be a particular continent, let's say Europe, to just the northern hemisphere, to the entire planet. Now, the context I'll be talking about today and what is in the news and in conversation now is global climate change and the temperature change increase in the global temperature we're currently experiencing. So what is climate change? Well, it happens on all sorts of scales. One scale that we have seen in history, in recent history, is volcanic eruptions. In particular, the Laki volcanic fissure erupted in 1783. And when that happened, it created a shroud of ash and sulfate aerosol that covered pretty much all of Europe, Northern Asia, parts of North America, and the such. Basically, that black circle that you're seeing resulted in a 1 to 3 degree temperature drop in the mean temperature in the northern hemisphere. The sun intensity lowered dramatically. Many writers of the time took note of this particular weather phenomenon. And at the same time, certainly the year the eruption occurred, winter came early, and this resulted in many crop failures and mass famine and starvation across these areas. The bottom line is this was a volcanic eruption changing the mean weather over the scale of about 10 years, but once Laki stopped erupting, returned back to what would consider the long-term normal. On a longer scale, on a scale of 200 to 400 years, especially in the northern hemisphere, were the medieval warming period and the Little Ice Age. Both of these well documented both in Europe and from paleoclimatological data and sediments, tree rings, and the like. But the bottom line is, and then you can see to the right, the red line is actually the temperature that we're currently seeing, a temperature increase we're currently seeing in relationship to those warming and cooling periods. But the main point of this is warming and cooling has occurred on this planet, whether it's a 10-year scale or hundreds of year scales. And as in the next slide, essentially through the history of planet Earth. The baseline in this graph, the zero line, is the average temperature between 1961 and 1990. And what it shows is temperature anomaly. And these temperature anomalies were derived from all sorts of sediment, rocks, microfossils, ice cores, all the paleoclimatological research has gone into this, and mostly forced by orbital changes, changes in the intensity of the sun, changes in greenhouse gas levels, and changes in the albedo of the planet Earth, its ability to absorb or reflect light. But what I wanted you to note is that just a 2 degrees Celsius drop in our temperature from current temperatures, 2 or 3 degree drop in the temperature, mean temperature of the planet Earth, and we descend into an ice age. Major cities in the northern hemisphere would become unlivable. Also, and that's I have a major ice age mark there. Also, further in history, 50 to 60 million years ago, evidence indicates that the planet Earth was 6 degrees Celsius or so warmer than current temperatures. And in that case, it's thought that the planet Earth had no ice on the surface. So you can imagine how different the weather patterns must have been in those two scenarios. And that's why mean temperature of the planet is so important, because it reformats the weather patterns that we see. And our history means nothing, especially our short-term history of 100 and 200 years, in the context of a changing temperature profile of planet Earth. And so, 50 million years ago, a planet Earth without ice. That's 9 degrees Fahrenheit warmer. 1.8 million years ago, mile thick ice sheets as far south as New York City. Only 5 degrees cooler, mean temperature of the planet Earth. So 1 or 2 degrees Celsius, 2 or 4 degrees Fahrenheit, doesn't sound like that much on the face of it, but it does essentially change the weather patterns on planet Earth, and that definitely impacts what we do as human beings heading forward. So what I wanted to show you is, taken independently, maybe there can be some argument about the fact that the planet is warming. But there's overwhelming evidence, I'll call it the climate change fingerprints, that our planet is currently in a warming state. And that's without considering anything else. This is just looking at observational evidence that we have right here now today. So what are those fingerprints? And I'm by no means showing them all, but a decent cross-section. One of the most important, the ice is melting. The Arctic sea ice extent continues to decrease. The orange line that you see is basically from 1981 to 2010, the median extent of the sea ice minimum. Sea ice minimum occurs every September. And that's the mean extent from 1981 to 2010. This white area, is the sea ice extent for last year. And last year has largely been deemed a recovery year. And as you can see, the sea ice was not even able to recover to its long-term mean. And in fact, the previous 4 or 5 years was substantially smaller than the white area pictured in this image. This trend is expected to continue. The Greenland Ice Sheet is melting. In 2002, they put up a polar orbiting satellite called GRACE. That's an acronym for Gravity, Recovery, and Climate Experiment Satellite. NASA and then I think the German Space Agency were involved in this. But the bottom line, it's a pair of satellites that continuously measure the distance between each other using lasers. Knowing what we know about mass and its relationship to gravity, is the changes in the distance between these two satellites and their speed tells us something specifically about the mass change going on underneath the satellites on planet Earth. So looking at this trend, in 2002, Greenland was actually experiencing a mass of ice increase of 1,000 to 1,500 gigatons per year when they started this program. Now, fast forwarding to 2013, we're actually losing ice at the rate of 1,500 gigatons per year, but from the looks of the graph, accelerating. So in our lifetime, Greenland was gaining ice and now is losing ice at a increasing pace. But it's not only Greenland, Antarctica is losing ice, the ice sheet on land. When they first launched the GRACE satellite, it was gaining about 500 gigatons a year. Now it's estimated by a number of independent sources that it's losing about 500 gigatons of ice a year. Now the eastern Antarctica ice sheet it's fairly stable right now. It might be losing a little, but it's pretty small. It's the West Antarctic ice sheet where the ocean has warmed just about the most, and the warmest surface temperature, the warmest surface temperatures are being observed, where the most of this melting is occurring. But not only that, the glaciers are melting. And certainly in recent times when, as you can see, the bottom graph with the red dotted line is the reference glaciers they're using, and they cover every continent, almost every location on planet Earth. And the top graph is actually the mass loss of the glaciers in total. And what you see over time, especially since the time of a decent number of reference glaciers, is that melting has been increasing. This is a sure sign that the planet is warming. But more than that, the ice constitutes a very small portion of our planet Earth and where the heat's being absorbed. The oceans continue to warm. And more confirming data comes in with each day on this one. Back in 1960, 1970, it could be said that most of the observations are probably surface sea temperature observations, certainly not very deep. But as time has gone on in the last 10 years, they are taking observations as deep as 2,000 meters, over 6,000 feet deep. And those measurements are conclusive. The ocean continues to gain heat content. You can see that looking at the red line here is that it's gone pretty much unabated over the last few years. And in fact, if you look at the very last part of the curve, actually may have even increased in recent times based on these measurements, and not just surface measurements, measurements through a deep layer of the ocean. So what's all this mean? Melting ice, warming ocean? Well, the sea level is rising. Thermal expansion of the water, additional water flowing into the ocean, is rising this sea level. And if you look at the line that I've drawn, perhaps the fastest sea level rise in recorded history using tidal gauges and satellite measurements, perhaps the fastest rise in sea levels we've experienced in recorded history. And it makes sense if the oceans are warming and the ice is melting faster. But not only that, land and sea surface temperatures are rising. This is, once again, we've got a baseline from 1901 to 2000. And these are anomalies. And it's basically a measurement of both land and sea surface temperatures put together. The blue being a negative anomaly below the long-term normal, and the orange or red being above the long-term normal. And as you can see from the line that I've drawn, is the warming continues unabated through time. When you look at it through the time scale, you need to look at temperature change, an average temperature change of the globe. The bottom line is that it continues to warm. There may be some wavers and wiggles along the way, but when you step back and look at the big picture, our sea surface and near surface temperatures are warming across the planet. But just as important is if we look at temperature extremes and the distribution of temperatures. And what do we see there? And this is this study was done for the Northern Hemisphere and Northern Hemisphere sites. In 1951, from 1951 to 1980, and that's the graph on the left, you can see they've basically produced a normal distribution with the blue temperatures being below normal temperatures, the white being near normal, the red being above normal temperatures. And so that was the distribution through that 30-year period. Now fast forward all the way to the right to 2001 to 2011. And once again, this is the Northern Hemisphere. Make note of the green line as the distribution from 1951 to 1980. When we plot the distribution of the last 10 years, compared to the 1951 to 1980 average, 2/3 of the temperatures observed, high temperatures, or not necessarily high temperatures, high and low temperatures, are above the 1951 to 1980 average. There has been a dramatic shift to the right toward warmer temperatures of high and low temperatures being observed on the planet. And some as many as 4 or 5 standard deviations on the high side compared to that 1951 to 1980 average. Our extremes are getting more extreme. It's a warming planet. It makes sense. So what factors are influencing the observed warming? Because there's all sorts of fingerprints show that it's warming. So what are the factors that are looked at by scientists to determine what's causing this warming? Because there has to be something, a causative factor producing this warming. And you know, the elephant in the room is obviously greenhouse gases, but I'm going to just show you how the scientists go through this to kind of determine this. This is an image from the IPCC report. I think it was the fourth IPCC report in 2007. And it's basically a radiative forcing perspective. You've got anthropogenic forcing and natural forcing that's included in this graph. The red indicates a warming influence. The blue indicates a cooling influence. Of course, you have your greenhouse gases, CO2 and methane. You have ozone, which has actually a warming influence in the troposphere. We also have the effects of aerosol, which are cooling, and largely sulfate aerosol emanating from sulfur dioxide that results from the burning of fossil fuel, especially coal. So that has a cooling influence. The natural influence of any significance in the long run, in the time scale of 100 or 200 years that this graph is indicating, is really the changes in solar irradiance, and that has been a net slight warming. But when you look at all the cooling and warming constituents that the scientists consider significant in any temperature change of the planet Earth on a global scale, is the net result is warming. Even if you consider the error bar is quite large, even the negative side of the error bar predicts warming. And never mind, it could fall anywhere in there as far as the warming. And the warming is basically watts per meter squared on the surface of the Earth. But also, they look at models. So just from a physics perspective, it should be warming. But they also can look at it from a modeling perspective. And the bottom line is this. They take 25 to 65 years of well-sampled data, both on the surface and up in the atmosphere. They run the model over this period of time, and they compare the model results to observations, whether that observation be heat content of the atmosphere or surface temperature, whatever you want to compare it to. And what they do, there's a couple types of models. There's the dynamic models, which explicitly try to model the way the atmosphere of the planet Earth works. And what they'll do, they'll run it in a certain mode. Let's say greenhouse gases, everything is included. They'll run it a number of times that are called an ensemble with different tweaks to initial conditions to account for the uncertainties of past weather scenarios and come up with kind of average conditions. And what they'll do is they'll run those models and they'll take out greenhouse gases, or they'll make the solar insolation steady. And by doing this, they can see which factors contribute the most to and result in the model best predicting the warming observed. Another type of model is statistical or attribution models. And essentially what this does is it takes the atmospheric constituents and runs a multiple regression equation. And what they do is they come up with predictors for what best predicts either the heat content or the surface temperature observed in the data set. And by doing this, they can find the different predictors, and when they do this, whether they run the dynamic models and they remove greenhouse gases, or they remove solar, or make solar insolation steady, or put in El Nino, La Nina, take it out, all of it, or they do the same thing with the statistical linear regression or multiple regression models. When they do this, this is what they find, and this is each colored line is a different study. Some are done here in the United States, some in Canada, some over in Europe. People from all over, different formulations from all over the world. Some are dynamic models, some are statistical models. When they do that, human contribution to the warming observed in the data set cannot be modeled without the inclusion of CO2 and greenhouse gases. And that's where we stand. There's no current model that can predict the temperature changes and fluctuations we are seeing in our data set without the inclusion of greenhouse gases. And in fact, it's the studies range from 70 to 100% chance that it's completely human caused. You can see at the bottom here the two main factors affecting the heating are carbon dioxide and actually sulfur dioxide, like I said, once again, from coal burning. So in fact, it's actually, the theory going now is actually cooler than it would have been because of the burning of coal and CO2, which there's a certain amount of irony to that if you ask me. But also they looked at solar activity, volcanic activity, El Nino, La Nina. When they did that, the best you can say is it's just about a neutral effect over the long run. It hasn't really changed our long-term climate. The biggest impact on long-term climate are human-caused, according to the models. And like I said, if you go back and just look at it in the physical basis. So what is causing it? We see the planet is warming just from all the fingerprints. If we look at it in two different ways, the only model that fits is greenhouse gases warming our planet. And so what is left? What is causing, I'm sure you all have your ideas, and maybe just one idea, I don't know. But it's becoming more and more conclusive that humans are causing it. We measure CO2 itself, all sorts of gases in the atmosphere actually, all over the planet. It's not just one singular observation at Mauna Loa in the Keeling curve, which is probably the most famous. Now there's observation platforms all over planet Earth measuring these gases continuously. And the main point I wanted to bring out is this, and I think on my number, I have 2 parts per million in my graph here. I think that's a little low now, but I'm just going to go with that. We know that CO2, because of all these measurements we have around the globe, increases by 2 parts per million every year. That computes to 15 billion tons per year increase in CO2. We also know how much fossil fuel we burn. And the EPA estimates this, other countries estimate this, how much CO2 is put in the atmosphere from all this burning of fossil fuels. There's equations for it, and it's well understood. That increase is about 30 billion tons per year. We can run a simple mass balance equation. The change in CO2 comes down to CO2 sources and CO2 sinks. Sinks being what absorbs CO2. There's natural sources and sinks, and there's human sources and sinks. And that all adds up to the change in CO2. Well, if we put the numbers that I just showed on the top, the 15 billion tons increase per year, the 30 billion tons per year put into the atmosphere by human burning of fossil fuels into that equation, everything else in the equation is a sink. If you put it all together and just blindly look at that other part of the equation, it's a sink. That means that this 15 billion increase per year really only can be explained by the human contribution. And I think this is the simplest way to put it, but if you are interested, just look up isotopic analysis of CO2. There's carbon-14, carbon-13, and carbon-12. And that isotopic analysis also indicates that the percent fossil fuel carbon is increasing in our atmosphere over time. And that's more confirmation that it's coming from us humans. So I think, in summary, there are tons of fingerprints pointing toward the planet warming. Any individual one can be disputed, but there's so many that point in the same direction. You have to start to grasp that this planet is warming. Physical understanding and modeling point toward CO2 is the causative factor. Human activity in fossil fuel burning is resulting in the CO2 increase. We need to start to get together on this particular point. Humans are causing the CO2 and greenhouse gas increase, and it's warming the planet. At some point, we need to come together on this part so that then we can shift the discussion to impacts. Because our risk is growing, and our risk management needs to come into this. I don't think we can continue to ignore this trend that we're seeing in the data, and our time is growing short on discussing and planning now for the impacts that are sure to come if we change the temperature profile of the planet and basically reformat our weather patterns. Now Robert is going to give you, based on this warming scenario, what those impacts, what the model shows are going to happen in the southwest portion and portions of the United States, and how that will impact us. Thank you.
Okay, get this started. Okay, my name is Robert Bohlin, and I'm going to talk to you guys about climate change impacts. And I'm going to try to conceptualize this for you from a weather forecaster's perspective. I am not a climate modeler, but I'm going to educate you as much as I know about that topic after doing extensive research on my own. So the first image that I'm showing you here on climate change impacts, I'm showing you this for a reason. And we're going to talk basically about, the planet is, as humans on the planet, we're constantly burning fossil fuels. This is an image at the Earth at night, showing that fossil fuel burning continues day and night unabated, night after night, year after year, and the greenhouse production, gas production is accelerating as third world countries around the planet industrialize. So where is the global warming going? So let's just do a quick review here. Oceans are by far the largest heat sink. Now, this really surprised me when I was looking it up, but 93% of the total heating on the planet goes directly into the oceans. Only 2.3% is going into the atmosphere. So, a lot of the times people will refer to, hey, the global temperatures are, while still increasing over the past 10 years, they haven't really gone up a lot. Well, a lot of that is currently being explained with the climate scientists, how a lot of that's going into the oceans right now. So there's still a lot to be understood on how that exchange works, but the fact of the matter remains that the climate is warming and the oceans are warming. So we've seen how small changes in ocean temperatures impact large-scale atmospheric patterns. And we've seen that with El Nino and La Nina, where basically the tropical sea surface temperatures warm up ever so slightly, a couple degrees here, as compared to normal. And it totally changes the way our atmospheric patterns play out. So when we have El Nino for the southwest, that typically brings the storm track further south across the western United States, increasing our chances for rain and snow from January to March. La Nina typically pushes this, is the opposite. There's cooling over the tropical eastern Pacific, cooler than normal. And it typically pushes the storm track further north over the western United States, reducing our chances for rain and snow across the southwest winter into spring. So let's take a look at some impacts here. We've all heard climate change model temperature predictions. These are some right here with a 1961 to 1979 baseline. Basically, we understand that models use different CO2 emission estimates for the 100-year global climate modeling. Model output changes based on these predicted CO2 concentrations. So we have high emission, high amounts of CO2. That's one scenario. And then there's lower emission of CO2 scenarios that are used as inputs into the climate models. So the top two panels on this slide indicate a higher emission scenario. So these two panels here, okay? And then the bottom two are for a lower emission scenario down here. So we see different, lower temperature ranges with lower CO2 emissions. And then if we look at the left two panels that basically show temperature change projections through the middle of this century, and then the right two panels, top to bottom, are emission or temperature changes for the end of the century from 2080 to 2099. So realistically, I believe we probably should look towards the higher emission scenario, given that our global economy runs on fossil fuel burning. China, India, Indonesia, and other third world countries continue their carbon growth rates. Unless we invent a new carbon neutral method for creating energy, this trend is only going to be increasing. Therefore, you want to go with the higher emission scenario. So how will these long-term global temperature changes impact the Southwest? Well, let's look at the higher emission scenario. And we're looking at roughly in the Southwest, say an 8 to 9 degree Fahrenheit temperature increase by the end of the century. So now I want to take a look at how that temperature impacts may impact the polar jet stream, and which basically determines the main winter and spring storm track. So the jet stream runs along a thermal zone between the cold air to the north and hot air to the south. And that's your jet stream, or you can also call it a storm track. Essentially, this changes position in response to these changing temperatures. That's where I get in my conceptualization here. So the jet stream travels like a slow-moving wave across the northern hemisphere. The average north to south position in winter and spring determines the chances for rain and snow across the Southwest, because that's the prime driver is our winter storm systems. That's what gives us our rain and snow in the Southwest region. When the jet stream moves further north, say even in La Nina years, Arizona and New Mexico have much lower chances for winter or spring storms. Climate models are showing warmer global temperatures are actually pushing the jet stream further north on average. So looking at a vertical cross-section of the atmosphere, I promise this is my most technical discussion, but I have to mention it here just to conceptualize how this works. The Earth's surface is on the bottom of the graphic here, okay? So we can see the North Pole is on the left and the equator is on the right. So we're looking vertically in the atmosphere. So we see three large circulations through the depth of the atmosphere. There's the Hadley cell in the tropics. We have the Ferrel cell, which is kind of the mid-latitude cell where we get all of our winter storm systems. And then there's the polar cell up near the North Polar region. Now notice the polar jet stream here located on the northern side of the Ferrel or mid-latitude cell. This is the region where we see the winter storms coming into and spring storms coming into the Southwest. So notice the downward motion on the northern side of the Hadley cell. Downward motion kind of corresponds to drying and warming in the atmosphere. That's the physics of it. So this region roughly corresponds to 20 to 30 degrees north latitude. And the downward vertical motion underneath this region creates the largest desert regions on the planet. Now climate change models basically showing these impacts. So here's the dry region and here's the winter spring storm track. So climate change models are basically taking this this Hadley cell and expanding it further northward. So I'm going to do that here. So that's kind of what an exaggerated version of what the climate models are suggesting. Now I'm going to toggle them back and forth, like now, future, now, future. So as we can see, as the Hadley cell expands further northward, that drier air expands further into Arizona and New Mexico across the Southwest. And the storm track, as the jet stream moves further north, moves further away on average from Arizona, okay? Which means less chances for storms going forward. So meteorological studies are already showing these impacts on the average storm track movement towards the polar regions. This graphic shows a northward displacement of the average storm track or jet stream. 1978 is the mean position. That's the red line. And 1997 is, 1978 is the blue line, and 1997 is the red line here. So we can see the mean storm track from February, March, and April is already moving further north over the last couple decades of last century. The seasonal time period, well, let's see. Moving on. So climate change models projections for seasonal precipitation. That's what we're moving on to now. This map shows precipitation impacts from global climate change, merging results. Oh, wait a minute. Yeah, so this particular slide is basically showing the observed change in annual average precipitation from 1958 to 2008. So we're seeing a significant drying trend in Arizona, although there is some increase in moisture over New Mexico. So things get complicated here, and that's where when we're running climate models, when you're trying to take things off of a global scale and downscale it, it does become complicated trying to regionalize these climate models. So climate change model predictions at the seasonal level. Here we have a graphic that's showing the wintertime and the springtime. That's where I'm going to focus on the most. And this is kind of indicative of that storm track moving further north, where we can see the much drier signal in the winter over the southwest, and especially in the spring months. This hatched area basically represents the higher confidence. This graphic was created from 15 different climate models, kind of an ensemble approach where you blend them all together. And so where most of the models agree is where the hatched area is. And you can notice during the spring, that hatched area covers most of the southwest with a large signal towards less precipitation on that. So conceptually, how might this play out? Well, our view is imagine month to month. February becomes more March-like. March becomes more April-like, and April becomes more May-like. And in the southwest, that means the drier period of time in our spring dry fire season expands. Another way to look at this is increasing chances every decade for back-to-back dry winter-spring seasons. So it's not like this is just going to happen suddenly at the end of the century and we have plenty of time. This could happen next year or the year after that. Some could argue that the January that we had this year could be more likely that dry, warm January would occur more frequently as we move forward decade by decade. One back-to-back dry year, along with a bark beetle kill, could potentially change the forest along the Mogollon Rim forever. And this could happen next year. The chances keep increasing. This could happen 10 years from now. It doesn't have to wait till the end of the century. Case in point, been told about how the Bradshaw Mountains experienced some back-to-back dry years and some bark beetle kill that went in there and wiped out a large portion of the ponderosa pines. This scenario could easily be repeated further north, and it could happen sooner than we think. So here we talk about climate change modeling. It does get complicated, but we're going to talk about some regional downscaling of global climate models. And I'm just going to say I'm not an expert at climate models. My expertise is more in forecasting, but we look at models all the time. But I'm going to cover what I've found out about some of these models. Two main types of models that were already discussed, statistical and dynamic models. Strengths and weaknesses are associated with each type. These are some of the strengths. Statistical models are cheaper. They give you point scale output. Dynamic models run on supercomputers, and then you're modeling month to month for 10 years, for 20 years. It takes up a lot of computing resources to do that. It's very expensive. I really think dynamic models is the way to go, but this stuff represents the cutting edge of where the climate science is. It's trying to regionalize, try to downscale these global models. Here's some of the weaknesses associated with these models. Limited terrain effects from your statistical database. You can't really model the dynamics of wind flow over the Mogollon Rim, say, for example. And regional climate forcing, which is independent of the global model, is not applied with a statistical method. And that's where the heavy lifting of the computations come into play. And even now, that stretches our supercomputing power to run some of these dynamic models on a decadal timescale. So it's my belief that we should stick to the larger scale model impacts for now when we're looking at our decision making until the regional climate models are improved. Climate modelers may disagree with me, but that's my opinion. So this is kind of like what a regional downscaling model might give you with a higher emissions scenario. Focus on this model here to the right. They try to show in Arizona, say, some of the terrain effects there along the Mogollon Rim, the Little Colorado River Valley. So you get maybe a little different flavor of what might actually be more impactful than what the global model might show you. Kind of like having 200 vision, I guess, on a global model scale, or 20/20 vision with the regional model. The problem is if you can't model it, parameterize it, set it up correctly, set it up accurately, then it allows them for more error in that model run. Now I'm going to move on to soil moisture changes. So then we talked about how the atmosphere responds to climate change. Now we're going to talk about soil moisture. So let's say it rains a lot. Well, guess what? The sunshine hits the soil and evaporates a lot of the water. That's how it works. Well, when we add CO2 heating to that, you're going to heat up the soil even more, which is going to dry out the soil even faster. And especially as we have, as storm systems get, shall we say, the atmosphere warms, the cold air isn't going to come as far north. We're not going to get as cold storms. So in the Southwest, we're going to get more rain instead of snow, less snowpack, those types of an issue. So even if we've got a year where it rained a lot in January, that moisture in the soil wouldn't last because of the lack of snowpack into, say, March or April. So when you add the CO2 heating to that equation, you're just increasing the soil evaporation. So let's look at some studies that have been done on soil moisture changes. Here we have some modeling of the soil moisture with 14 different climate models that show impacts going out at the, basically towards the end of the century here. The stippling indicates areas of high confidence where 9 out of 11 of the, or where most of the models agreed. These models were using the emission scenario called RCP 4.5, which stabilizes CO2 emissions by 2100. So it's my belief that this might be underplaying the signal, and so if you believe that the emissions will be continue to go up and not stabilize by 2100, then you might think that there might be even more of a drying signal with this. So impacts to the Southwest region show roughly 10% or higher drier soils by the end of the century, and this affects plants and ecosystems. So higher CO2 emission scenarios, again, would likely result in a stronger drying signal. So let's kind of sum this up. So we're looking at a warmer Earth. We have two things going on conceptually: soil moisture changes and storm track changes. So we got warmer ground increasing evaporation rates, resulting in drier soils. And we got winter-spring storm tracks moving further north, less chances for storms, higher chances for back-to-back dry winters. Decreasing storm activity across the Southwest during the winter-spring period, less precipitation events, and higher chances for extended droughts. So we're going to talk about addition summary to the ecology side. Given the climate change forecast for drier soil moisture along with drier winters and springs, what can we say? Well, how quickly will climate and fire interact to change species and vegetation distributions across the Southwest? And believe me, I don't have all the answers for this. That's up to you guys. What land management methods should we start using now to ease this transition, given the fact that this could happen rather substantially in the next decade even? What happens if we plan for a drier climate, say thinning the ponderosas a little thinner than we normally would, and in 50 years the climate is less dry? Well, it probably wouldn't be as catastrophic as what happens if we plan for a no-change climate, and in 50 years the climate is significantly drier. We could see total ecosystems wiped out. And this is invasive species and bark beetle and native species. So, yeah, it's a problem. So I leave that for the ecologists. So that's it for my end. Xander?
Well, thank you both. Those are great presentations, and I think you guys did a nice job of laying out the facts and good preparation for the upcoming meeting. So we have about 10 minutes till the top of the hour, and maybe people can hang around a little bit longer. In a second, I'll go ahead and unmute the line, but we already have one question come in via the chat window, and you're welcome to put in more that way. So Robert or Darren, do you want to respond to Kurt's question? On average, what percentage of annual precipitation comes during monsoons during winter?
Well, I think that varies depending on your station. Locations around the Southwest, I know in Flagstaff we got several months in the summer that are pretty wet and it's pretty similar between winter and summer, but in other areas that changes. So because of our high topography, it really varies based on the station you're at. And there's some climate links on our website, weather.gov/Flagstaff, and feel free to go check out our climate section.
Okay, thanks. I will go ahead and unmute the line, and so you can speak out your question, or if you prefer to type it in the chat window, you can do that as well. I guess maybe while we're waiting, I'll follow on Kurt's question and sort of probe a little bit deeper and ask you guys to think about if that storm track is changing, how much of the drying that we're likely to see is due to the change in the storm track versus some of these other effects.
Well, the storm track or the jet stream moving northward, which I think is already being observed even when they take long-term means of the jet speed and jet position, it's actually weakened and already moving northward. Robert already said that what that means for us is less winter and into spring precipitation. What it says about summer precipitation, I would say we don't really know, because you might hypothesize that would mean we'd have more predominance of high pressure, and that might tend to open the door to monsoon rain. But it certainly means that the winter precipitation would be going down, and I would guess that when they show that drawing, maybe that's the biggest part of it. But I'm not completely sure.
Yeah, that would be something that the modelers would probably get maybe a better feel for. But that would be my assumption as well. That the spring season is highly dependent on how far south those storms get, and the monsoon season, I guess at this point, is kind of an open question.
Okay, great. Are there other questions out there?
I had a question. This is Pepe. So my question was, if you try to kind of explain to people in terms of what to expect, let's say the difference between now and 2050, I've heard people kind of using the analogy is that like Flagstaff, for example, at 7,000 feet, or Flagstaff or any other town at 7,000 feet, is going to be essentially like if you move 2,000 feet down the hill. So do you have a good analogy to kind of compare in terms of what it looks like at 7,000 feet or at 5,000 feet, or so how much is it going to change, and to put it into an elevational kind of gradient?
I guess I could start there. One way to conceptualize this would be if you took the same higher elevation station and you have maybe some higher elevation areas further south, towards Mexico. That would be, eventually the climate would become that, given the Hadley cell is moving further north, and the storms at the same time are moving further away. So that would be the best analogy, I think. Darren?
That sounds good.
Yeah.
That sounds good.
So you think it's better to compare it latitudinal than altitudinal? So for example, saying that if Flagstaff in 2050 is going to be the same as Prescott or Payson, is not right?
Yeah, the hard part would be how far south do you go, and I don't have those answers. That would be something, again, that at this point that you want to do some modeling of that, because it's not an easy linear equation. It's definitely very complicated.
Okay.
That's why we run the models.
And Susan Rich has typed in a question, and she asks, has anyone modeled how the contribution of additional carbon from more and larger wildfires will drive things?
Yeah, I'm not certain if anyone has modeled that specifically. I would hope that was modeled, but I haven't seen anything along that line myself. But that doesn't mean I have the all knowledge of all the papers that have been published. So that may be online.
Okay. And I know that there are, of course, two components there, because there's also wildfires do put a lot of black carbon up, which, as you guys mentioned, particularly where it lies on top of snow, can have a big impact. So there's both the CO2 as well as the ash. But maybe somebody on the line, another participant, has some suggestions there, and you're welcome to put comments to respond to these other questions in the chat window as well.
Yeah, I guess I would just add to that from the fire weather forecasting perspective. If you told me that there was going to be less storms, that February was going to be March-like and March was going to be April-like, I just tell you, be prepared for hellish fire seasons.
Other questions? We're coming up at the top of the hour here. So I think you'll have additional time to talk about some of these models and their implications at the conference itself. I mean, that's sort of the whole point here. This is preparatory to give you the facts, and we're going to encourage the rest of the conference participants to watch the video from today's webinar. So I guess what I'd like to do now is close it off and thank Robert and Darren again. Very important presentation, and you did an excellent job of keeping it simple enough to understand, but going into enough detail to be very convincing.
Right.
Thank you.
Oh, and maybe we can't resist taking one last question from Mary Stuver. Do you guys want to talk about the Atlantic multi-decadal oscillation?
Once again, that's probably we probably don't have that answer. We know the Pacific decadal oscillation is probably certainly having some impact on the predominance of drier years as of recent. But yeah, I'm not really as familiar with the Atlantic oscillation.
Yeah, I mean, there's a lot of these oscillations that play some modulating roles here, I guess I would say. But on the long term, we're talking about a forcing that is going to override all these other maybe like decadal forcing or year-to-year oscillations. There's more than just that going on with the Pacific decadal and the El Nino and La Nina oscillations. There's a lot of things that modulate the signal. But in the end, overall, the tide raises all boats, and the big tide we're talking about here, the one that the Climate Prediction Center is using for their above normal temperatures year after year is the global warming signal, and It's rather significant.
And the expansion of the Hadley cell northward and then the movement of the jet stream northward has been pretty firmly confirmed through modeling studies, although more study is being done. And that alone, not even worrying about any other oscillations, as a further north jet stream is going to mean drier conditions, especially in the winter, which leads into spring, and that's just critical. And I would guess it's kind of critical for the bark beetle, less snowpack, less time, that kind of soil moisture.
Yeah, but the time for action is now, I guess, is what we're trying to say. Any more questions?
Mary has a follow-up comment about predictions that perhaps this next coming decade will be a little bit wetter. And I've heard others say that as well. But I think obviously it's not a continuous, smooth increase all the time. And the context I've heard that in is an urge to take advantage of either the time we have, or if there's a wetter year, that's a time for action, not a time to sit back and relax.
Yeah, correct. Because our feeling here is that it's coming. It's almost inevitable. And like Robert said earlier, it's not going to be like you flip a switch. It's the odds of this drier scenario keep going up with each year, and once you tack on 50 or 100 years, those odds go up substantially. Where in a 20-year time frame, you're likely to see it, whereas now, maybe not so likely, as far as like dry winters in a row. Those odds are increasing with the further north jet.
But I think, and I think I'm glad Mary brought this up, because we may have some opportunities, some reprieve where we can get some work done, and we need to take those when we get them.
Yeah, we need that PDO to change sign. I think that would help right there.
Right. Well, thanks again, guys. I'll let you go now, and if anybody on the line wants to share this conference, this pre-conference webinar with their peers, we'll be sending out a recording shortly. So thanks again, everybody.
Right. Thank you.
You.
Thanks.